In this video, we will study about KMP or Knuth-Morris-Pratt algorithm for pattern matching in strings. So here we will see it in depth. We will see why this, what is the intuition behind this algorithm, and we will also see in detail how to construct longest prefix suffix array, which is an important component of this algorithm. And we will also see intuition behind why we are building it in that way. So we will see all of that in detail, and in the end we will also implement it in one of the languages. And we will see an example. So let's begin. First, let's start with a naive pattern matching. Let's say you are given this text and you have to match with this pattern. So we are talking about naive algorithm. And let's say the text length is n and pattern length is m. So how you will match it? You will place the pattern here. You will try to match character by character. So A matches, B matches, A matches, B matches, A matches. Now a mismatch happens. So we know that we have not found it yet. So what we will do next, we will shift the pattern here, A, B, A, B, A, C. And we see that here it mismatches at the first character itself. So we will shift it again, A, it matches, or you can see here only, we are here, A matches with A. So we go next character, B matches with B, A matches with A, B matches with B. Then we have a mismatch here. So again, all of these efforts are going in vain. You saw that in the first time we matched till here, and then we found a mismatch here. And again we are starting from here, again matching a few characters, and then in the end we are finding a mismatch. So what can be the worst time complexity of this approach? Ultimately you will find it here. You can see that A, B, A, C is here. So you will shift one step, and wherever you find mismatch, you again shift by one step. So you are placing this pattern or trying to overlap with this. So first you overlap here and see if each character is same or not. If it's not same, you shift this window by one step, and here this window will perfectly overlap. So it will work always, but the time complexity can be of the order of nm. Because you may have to match of the order of length of pattern, and you will do it n times because you are shifting by one step, and the pattern may be in the end, or even if it's not in the end, you are asked to find all the occurrences of the pattern, so you have to go to the end anyway. So how can we do better? This looks like a bad time complexity since text can be very long, and pattern, if it's also, let's say, 100 characters long, then it's 100 times the text. So there KMP algorithm comes in. So what this algorithm tries to say is that instead of shifting the next match from the next character, that is, instead of shifting the pattern by one step, you can shift by more steps. And how many steps, that we will calculate using the longest prefix suffix array. So first of all, let's say we are allowed to shift the pattern by some steps. Let's say this is the text. We don't know the beginning or end. We are somewhere in the middle. And we have a pattern, and the pattern starts from here and it continues. So currently this pattern is here, this window is here, and we matched a few characters, and here we found a mismatch. So this character is not matching. Everything else was matched. It mismatched here, just like our earlier example. So let's say text is not given to you. Although here it's given to you, but let's forget. Let's say somebody says you that I was matching this pattern with a text and I found a mismatch here at index j, and this is index I or I and j. So what can you say about the text even without looking at the text? The first mismatch occurs at jth index. That means the previous character was matching here, this was also matching, this was also matching, this was also matching. So previous j-1 characters of the pattern was same as the previous j-1 characters of the text. So if this is I, then this will be I-1, and this will be I-j plus 1. So from this till this, it was same as this. So let's say we have calculated this array using which we can determine how many characters to shift. In naive, we are shifting by one step. But here, let's say we are allowed to shift by some steps k. So we shifted by k. So this length is K. So what can we say here? If we have shifted by K steps, then this part should be same as this part. Otherwise there will be a mismatch. Why would we shift like that? Or we would not gain anything here. So let's say we shifted by K, and now this part should match with this part. So what is this part? From here to here, it was J, or if you go one step back, it was J minus 1. And this to this is K. So you know this part. This part is X. K plus X is J minus 1. So this is a prefix of this pattern. You see that this pattern starts here, and this is the current position where we are considering in this text. So this is the prefix of the pattern, and this is the suffix of the pattern. Since this part matches with this part of the text, this part was same as also this part. So this was originally the suffix of this pattern before this character. And now this is the prefix of the same pattern. Pattern is not changing. So we are trying to find the longest suffix, which is also a prefix of the substring before this, before the mismatching character. And we are trying to find proper prefix and suffix. Otherwise, proper prefix means that you cannot include the last character. All the prefixes excluding the last one. That's why proper prefix. If you take the complete string, that is a prefix, but that is not proper prefix. And why we are adding this constraint? Because if you take a string, the complete string itself is a prefix, and the complete string itself is also a suffix. So you will always find this, whatever is the length of the string, as the longest prefix, which is also a suffix. That's why we are adding proper here. So let's say we know this, that for this character, what is the longest prefix that matches with a suffix, then we know the shift. After all, this length is X, the length of LPS I, or here it's J, so let's write LPS J is equal to X, this thing. So if we know this X, then we know by how much to shift, because we can calculate by J minus 1 minus X. You will get the K, and by how much we want to shift. And why we are asking for the longest? Because if we take the smallest, let's say this is A, and here also it's A. Then if we shift it directly here, so this A will match with this, so it's valid. But we may miss some patterns here, so we are looking for the longest such value. If we can extend it further like this, we will take that. So this way we will not miss the pattern. Now the question is how to calculate this LPS array in the code. By looking at it will be easy, but how to calculate that? So let's write the pattern. It was A, B, A, B, A, C. A, B, A, B, A, C. So for first character, it will be 0 always. For second, now it's AB. So in AB, what are the prefixes? Proper prefixes, just A, and proper suffixes, just B. So there is no match. So it's again 0. If you look at this part, so what are the prefixes? Proper one, A and AB, and suffixes are A and BA. So this is a match of length 1. So here it will be 1. If you look at this index, these are I, 0, 1, 2, 3, 4, 5. So this is AB, this suffix, and this prefix is AB. So it will be 2 for this case. Then if you look at this part, it's ABA, and here it's ABA. So let's write it's A, AB, AB, A, and AB, AB. These are prefixes, and suffixes are A, BA, ABA, BA, BA. So this one. So here it's 3. Here it will be 0. There is no C here, so nothing will end at C. so it's 0. Now we have this LPS array. We will see how to build it in the code. So let's say we have this LPS array, then how to use it. So first we will try to match it here. So A, B, A, B, A. Let me clean this and write this LPS 0, 0, 1, 2, 3, 0. This is LPS. So mismatch happens here, that is at C, this index. So here this LPS is 0. This 0 means that there is no prefix in this part, which is a suffix also. So that means we will shift entirely here. So we will directly jump till this point. So mismatch was A, B, A, B, A, C. Here it was mismatch. So we will directly start from here. So we will shift the pattern here. 1, 2, 3, 4, 5 steps. So next we will write A, B. So here mismatch is in the beginning only. So beginning is always 0. So we will start after this. A, B. And again in the beginning. So next we will come here. A, B, A, B, A, C. Again mismatch is here. So we will start from here. A, B, again beginning. So we will start from here. Then here. So next we will put it here. A, B, A, B, A, C. And this way we will find the pattern. So here we are saving on some repeated comparisons. And the time complexity will be O of m plus n. Now the main task is how to build this LPS array. So let's try to build for this case. So here we had built it manually by looking at the pattern, but how we will do it in the code. So the pattern is A, B, A, B, A, C. So what we will do, clearly we will start from 0. The first index is always, the first LPS is 0. So this is known. Here I am writing the indices. So we will start from here. I will be starting from here onwards. This V0, no, for granted. So here what we will do, we will write it like this. So let's say we are writing I equal to 1 to n minus 1. 0 is done. So this is the range of I. So what we will do, we will have another j. And while j is greater than 0, and this, let's call it P for pattern. Pi is not same as Pj. So let's say first case is that Pi is same as Pj. So let's say this is the pattern. And we have calculated the LPS of all the values, and we are currently calculating the LPS of ith index. This is the index that we want to calculate. What is the LPS for this? That is, what is the longest prefix, proper prefix, that is starting from here till some value, which is same as this k length. So this is prefix, this is suffix. This we want to calculate. We don't know the k, but we have calculated till I minus 1. Now we will use that to calculate I. So let's say for I minus 1, that is this index, the LPS was LPS I minus 1, which we are capturing in j, you can see it here, was j. So this was the length of LPS for I minus 1. So what does that mean? That this part is j, the length of this part. This should be same as this j. So this last index will be j minus 1, because we are starting from 0. So this entire length is j. Now let's see it carefully. So this part is, these j characters are same as these j characters. Now what if this next character, this was j minus 1th character, and this will be jth character, or rather j plus 1th character at index j. This is same as this one, the current character for which we are calculating the LPS. Then this complete thing from here till here will become same as this part. So this length will be j plus 1, this length will be j plus 1. So this is the easier case. So if pi, this is p, is same as pj, then LPS I equal to j plus 1. This is the simpler case. But the other case is that what if this was not equal to this, then what we will do? So let's see this this second case carefully, that is this character is not same as this. If it's same as this, it's very simple. We just, this part will also become same as this, so it will be j plus 1. The tricky part is this one, and here I don't find any good explanations. They just take it for granted, this writing in the code. So this part, this j was matching with this j, and this is index I in the pattern p. So this does not look like equal. Here, so this part is same as this, and we know that this character is mismatching. So this character here, pj, is not matching to pi. So we could not find this kind of suffix. So what we will do, we will find some smaller suffix. Since this was the best case, the smaller suffix would be something like this. It will start here and end somewhere here. And this will be the prefix here. So it will be same as this. But we don't know what is this difference. This is clearly index, this point is index j minus 1. But we don't know what is this part or this length. But we know that this will be same as this, what we are looking for. That will be the LPS for this ith one. So let's see. So this was matching with this, and this in the blue one, this part is same as this part. So if you come here, this part is same as this part. So let's call this length as L. The length of this yellow substring is L. So this is L. And this length is j, and this j is same as this one. So let's ignore it for now, and let's look at this one, the beginning one. This is j, and this part is same as this thing here. So I have drawn it separately. These are same thing, you know why. So this blue is same as this. I have drawn it separately now. So and this is same as this. So this yellow part is same as this. So what is this? This yellow part would also be here. Let me draw in some other color, white. So this white and yellow are same because these two are exact replica of each other. These two, these j characters. So here this suffix of length L, and here it's prefix of length L. So suffix here is same as suffix here. So this also L. So this suffix is same as this prefix L. So what will be this value L? This will be the LCS of this character, whatever is the character here. So LCS of this character. And what is this j? In fact j. So here we are at j minus 1. So LCS of j minus 1. So if we know the LCS of j minus 1, we can know this value. So that's why when pi is not equal to pj, then what we will do, we will write we will move j here. So we have to move here, and then we will compare the next character with this one, current one. If they match, then we include this. If they don't match, again we will continue repeating the process. So if this is not same as pj, which is the case, then j equal to LPS j minus 1. This is the LPS of j minus 1, this length. And again here we look for if this matches with this current. So here I have drawn it wrongly. This yellow should not infiltrate in this I. So let's call this I is here. This is still I minus 1. This yellow is within this blue only. So before I, that is. So again, if this matches with this, we will return j plus 1, or LPS of I will be j plus 1. And if it doesn't match, then again j equal to LPS j minus 1 until we reach the beginning. In that case, we will match. If it matches, it will be 1. If it doesn't match, it will be 0. So that is the main part. So once you have this LPS array, we know how much to shift. So it will be, so this LPS denotes this part. The shift will be this part, which is current index minus LPS of index minus 1. So now let's write the code for this, and we will run through an example. So this is the same example that I had taken. So let's first build the LPS array. M is the size of pattern. And N is the size of text. Next, it will be of the same length as the patterns and initialized to 0. So 0th index is already initialized to 0, so we can start from 1. So this is the LPS I minus 1. This thing. So for calculating the LPS of I, we find the LPS of I minus 1. So we know that this part is matching with this part, this J. J denotes that thing. So this is the tricky part, the other one. And this will build the LPS array. So if this mismatch does not happen, then LPS I will be, then this condition will be true. PI will be same as PJ, then LPS I will be j plus 1. We have incremented j. Otherwise, we go to LPS j minus 1. And we saw the logic here. This part is same as this part. So this part is same as this, and this index is j minus 1. So this length L denotes not LCS but LPS j minus 1. So we are moving j here from here to here. Again, we will do the same thing. We will try to match the next thing with the ith character. If it matches, good, j plus 1. If it doesn't match, again look for LPS of j minus 1, and it will repeat until we reach the beginning, or we find a matching value here to the ith character. So this is what is done here, and this is the equality case. So now LPS array is built. Now we will start matching the text and pattern. So I is for text, index in text, j is in the index in pattern. Initially we will start with first character of each. I less than n. So we have to find all the occurrences. Pj is same as ti. Then simply we will keep incrementing indices in both. So I plus plus j plus plus. And let's say we have reached the end of the pattern. How we will know that? The last index is m minus 1. Maybe this was the last index j. So now it has become m. So if j is equal to m, then we found this pattern. I minus j. So we are returning the beginning of the pattern where it matches. So if this is the text and let's say it matched here, so j will be here at this point, j minus I is here, so I minus j, that is go j steps backward and return this index. And we have to continue the search, so we will shift this pattern again. So mismatch occurs after j matches in this case. So here it was a match and this is the mismatch case. J is less than L and Pj is not equal to Ti. So what we are doing here else means j is 0. So the first j and I are the pointers in text and pattern. So j is already 0 and this also denotes the length of the longest prefix, which is a suffix. So we are already in the beginning of the pattern. So nothing to do here, just increment 1 in the text. And here if j is not 0, then j is LPS j minus 1. So we shift the pattern such that, so we shift it by this amount, j amount, not exactly j but this other amount. So this is the text, this is the pattern, we have seen this. So LCS was j means this one. So this part is same as this, so when we shift, this will come here, this j. So this will already match with this, so we keep j here at LPS j minus 1. So we will start matching from here. This part no need to match, it will be same here. So if you have confusion here, just see a few minutes back, I have already discussed this in detail. And I think this should work. Let's try to run this. So it says found at index 14. So it's 0, 1, 2, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So this is where match is found. So I hope you understood it. Try to watch it again and again until you understand it.